General relativity, step by step. We've reduced the Einstein field equations down by taking a linear approximation to this rather nice form here. So we've got two things to consider. We've got the Einstein field equations here, which are written in different notations. We can use this quad notation here, we can use this kind of classical notation here, or we can use the di-alpha notation here. What have we got? We've got the equations themselves, and we've got the gauge condition here, which we've imposed separately. Okay, so what I'm going to do is just write these equations out. We've got a di-alpha h bar mu nu equals 0. And I'm going to find, motivated by this form of equations here, what I'm going to do is I'm going to try solutions that look like this. I'm going to have a constant matrix there, but we need two upstairs indices times some wibbly wobbly things. Wibbly wobbly things. Things that wiggle. After all, we're considering waves. So what I'm going to do is considering a mu nu times x of I k alpha x alpha. I'll just spend a little bit of time. That's constant. This thing here is a constant, and k alpha is a constant second rank tensor. Two upstairs indices, and this is a constant 4 vector. Constant 4 vector. I guess that should be a C. Constant. Just a word about exponential notation. When I say x of ix, that's equal to e to the ix. That's equal to cos x. This is Euler's formula, I think. Cos x plus I. No, De Moivre's formula. Plus I sin x. It's understood that we consider only the real part, and we ignore the complex the imaginary component. The reason for doing this is that if you deal with cos and sin separately, you're always going over and over again. You're using cos and sin and cos, and here you're just using one function, which is so much easier. What I'm going to do is just look for solutions of this form, and then I'll try and interpret what the terms mean. So where's my equation? It's di-alpha. So it's no, I can't have a repeated end. I'm going to call that beta. Di-beta acting on a mu nu x of I k alpha x alpha. And this equals 0 by the Einstein field equation. I'll just pinch in a bit. Okay. So it's di beta. I'm going to change notation a little bit. That's di by di x beta. Actually, there's something I need to do first. What I need to do is to observe that this guy here is constant, and so it can move to the left-hand side. So a mu nu di beta e to the I k alpha x alpha equals 0. We've just observed that this is constant. This thing here is constant, and so it commutes past our differentiation. Now, if that's the case, and if I assume that my tensor here is not equal to 0, I can just cancel it out, because the right-hand side equals 0, so I just know that this term is equal to 0. Well, that's nice. You see how I'm gradually simplifying it? I'm gradually simplifying it. Let me write it out now as di by di x beta. I'm sort of... I'll put the summation convention in of exp of I, and then that's going to be k0 x0. See, there's an implicit summation over alpha, plus k1 x1 plus k2 x2 plus k3 x3. I think that's another round. We've got quite a lot of brackets to close. There we go. And all this thing equals 0. Blah, blah, 0. Right. Now, when we differentiate with respect to x beta, it doesn't matter what beta is. Beta, let me just put another bracket in there. Let's put a big bracket there. Actually, I'll make it a curly bracket. There we go. Make this one a curly bracket. I'm just going to consider what happens inside the curly bracket. You'll see that as far as differentiating with respect to x beta is concerned, whatever beta is equal to, it just picks out that particular term. It could be, if beta equals 0, we get this term, and all the others are constant because it's curly D. If we pick out beta equals 1, we get this term. If we pick out beta equals 2, we get that. If we pick out beta equals 3, we get that. So the die by die x beta picks out just that component, and we can write that out dead easily. Sigma from beta equals 0 to 3. Die upstairs beta, which I'll expand later, I'll keep that in there. And that is going to be, of course, if you differentiate the exponential function, we just get k subscript beta. Oh, that's multiplied by I, because whichever one it is, it just picks out that term, times x of I k alpha x alpha. I'll put the summation back in. Is that right? I've got beta summed here and alpha summed inside there. Equals 0. All right. Now I observe that these guys here are constant, so they go outside the summation. Oh, in fact, they not only go outside the summation, they go outside the summation and the differential. So we are left with I k subscript beta. Oh no, it doesn't go past the summation. The summation's got to be here. I guess the I can go outside. K beta die beta. See, the summation just takes care of itself. Of is that right? Yes, of course it is. This is constant. I was a little bit worried that I'd miscommuted, I guess, that k there, but k is a constant. Times e to the I k alpha k, no, not k, x alpha, there it is, close brackets, equals 0. Oops. This interface is going to drive me nuts. Where are we? What on earth's this? What on earth's this? Oh, that's the that's the Riemann-Christoffel tensor, isn't it? Hang on a minute. Right, where was I? Here we go. This interface is going to drive me crazy. Right, and we can do the same thing again. That's beta equals 0 through 3. That's I. This term here picks out only the one we're interested in, and we've got k. Oh, actually, no. What I'm going to do first is I'm going to bring that down to a low to the downstairs place. So we've got this I here. We've got k beta down there. We've got eta because I'm only considering linear approximations. That beta is there. That gamma is there. Die gamma e to the I k alpha x alpha equals 0. Good grief. Yeah, I think that works. Okay, so this thing here is constant and it goes outside. No, it doesn't. I'm going to leave it exactly where it is. It doesn't pass. I'm going to ignore that though. I'm going to get rid of that and I'm going to rewrite my I there. So we've got I k beta gamma, and then here we've got the same thing. We've got I k subscript beta times e to the I k alpha x alpha close square brackets equals 0. I times I is -1 times, I'm just going to reorder it a little bit, beta gamma k beta again. There's no problem with this. It looks what have I done wrong here? Ha, yes, that should be a gamma. Took me a little bit of time to spot that. So that's going to be a gamma e to the I k alpha x alpha equals 0. Now, of course, the modulus of that equals 1, so I can just ignore that. The modulus of this is equal to 1, so I can just ignore those two terms there. I've got eta beta gamma k beta k gamma equals 0, or k beta beta, no, it's k beta equals 0. How about that? What a beautiful set of reductions. Let me just go through this whole set of thinking again. Let me just go through the whole of it now. I'll pinch in a little bit because I don't need to write. We've got the wave equation here. We're looking for solutions with a wibbly-wobbly component and a constant component. That we might not find any, but we're going to look for some. If there are any solutions, then they've got this property here, which expands to that, which expands to this, which expands to that, which expands to the other, blah, 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 blah. It's quite difficult to keep your focus on everything, and we get this beautiful relationship, k beta equals 0. So let me just, well, actually it's easier to think about this one here. Eta alpha beta, let's say, k, which way around do we do it? Do we do it contravariant or covariant? We may as well do it that way around. K beta equals 0. So because the flat space metric is 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, that's eta. What we have here is minus k0, k0, plus k1, k1, plus k2, k2, plus k3, k3 equals 0. How about that? I'll interpret it in the next screencast. But for the moment, we've got this beautiful, beautiful relationship, which I'll talk about in the next screencast. Stop.